Good morning everyone. In the previous lecture we saw how to fit a linear model between two variables x, which is the independent variable, and y, which is the dependent variable, using techniques called regression. And in this particular lecture we are going to assess whether the model we have actually fitted is reasonably good or not. There are many methods for making this assessment. We will look at some of these. So, what are the useful questions to ask when we fit a model? The first question to ask is whether the linear model that we have fitted is adequate or not, is good or not. If it is not good, then perhaps we may have to go and fit a nonlinear model. So, this is the first step that you will actually test whether the model is good or not. Then even if you fit a model, you may want to find out which coefficients of the linear model are relevant. For example, in the one variable case that we saw, one independent variable, the only two parameters that we are fitting are the intercept term beta naught and the slope term beta 1. So, we want to know whether we should have fitted the intercept or not, whether we should have taken it as 0. When we have several independent variables in multilinear regression, we will see that it is also important to find out which variables are significant, whether we should use all the independent variables or whether we should discard some of them. So, this particular test for finding which coefficients of the linear model are significant is useful not only in the univariate case, but more useful in multilinear regression, where we want to identify important variables. Suppose the linear model that we fit is acceptable, then we want to actually see whether we can improve the quality of the linear model. When fitting a linear model using the method of least squares, we make several assumptions about the errors that corrupt the dependent variable measurements. So, are these assumptions really valid? So, what are some of the assumptions that we make about the errors that corrupt the measurements of the dependent variable? We assume that the errors are normally distributed. Only this assumption can actually justify the choice of the method of least squares. We also assume that the errors in different samples have the same variance. This is called homoscedasticity assumption. So, we are assuming that the errors in different samples are also having the same variance. In general, these two statements, assumptions about the errors, that they are normally distributed with identical variance, can be compactly represented by saying that epsilon I, the error corrupting measurement I, is normally distributed with 0 mean and sigma squared variance. Notice that sigma squared is same and does not depend on I, which means it is the same for all samples I equals 1 to n. That is the assumption we have made when we use the standard method of least squares. Now, we also assume that all the measurements that we have made are reasonably good and there are no bad data points or what we call outliers in the data. We saw that even when we are estimating a sample mean, one bad data can result in a very bad estimate of the mean. So, similarly in the method of least squares, if we have one bad data point, it can result in a very poor estimate of the coefficients. So, we want to remove such bad data from our data set and improve, maybe fit a linear model only using the remaining measurements, and that will improve the quality of the linear model. So, these are some of the things that we need to actually verify. These assumptions what we have made about the errors, whether they are reasonable or not, if there are bad data, can we remove them or not. And so, we will look at the first two questions in this lecture, which is to assess whether the linear model that we have fitted is good and how do we decide whether the coefficients of the linear model are significant. So, before we start, we need to derive some properties of these estimates that we have derived. Remember that the coefficients of the linear model that we have fitted, which is the intercept term beta naught and the slope term beta 1, these are obtained from data, from the sample of data that you are given. We have indicated that these are estimates and not the true values by putting this caret term on top of each of these symbols, which means that this is an estimate, beta naught hat is an estimate of the true beta naught and beta 1 hat is an estimate of the true beta 1, which we do not know. However, we can prove based on the assumptions we have made regarding the errors, that the expected value of beta naught hat will be equal to beta naught. What does it mean? If we were to repeat this experiment, collect another sample of n measurements and apply the method of least squares, we will get another estimate of beta naught. Suppose we do this experiment several times and we will get several estimates of beta naught hat. Let me average all of them, and the average value of that will tend towards the true value. That is what this expression means, that if we were to repeat this experiment several times, the average of the estimates that we derive will actually be a very good representation of the truth. Similarly, we can show that the expected value of beta 1 hat is equal to the true value beta 1. Notice that beta naught and beta 1 are unknown values. We are only saying that the expected value of beta 1 hat will be the true value and the expected value of beta naught hat will be the true value, and such statements are also known as, if the estimates satisfy such properties, we also call these estimates as unbiased. There is no bias in the estimate of beta naught hat or beta 1 hat. The second important property that we need to derive about the estimates is the variability of the estimates. Notice we get different estimates of beta naught hat depending on the sample that we have derived, and therefore we want to ask what is the spread of these estimates of beta naught hat and beta 1 hat if we were to repeat this experiment. We can show again through based on the assumptions we have made that the variance of beta 1 hat will be equal to sigma squared by Sxx. Sxx represents the variance of x, or x minus x bar the whole squared summed over all the samples, whereas sigma squared represents the variance of the error that corrupts the dependent variable y. So, sigma squared is the error variance, Sxx is the variance of the independent variable. So, this ratio we can show will be equal to the variance of beta 1 hat. Similarly, we can show that the variance of beta naught hat is sigma squared, which is the variance of the error, multiplied by this ratio. The numerator is the sum squared values of all the independent variables, while the denominator represents the variance of the independent variable. Okay. In this, the Sxx can be computed from data, sigma of xi squared can be computed from data, but we may or may not have knowledge about the variance of the error which corrupts the dependent variable. That depends on the instrument that was used to measure the dependent variable. If we have some knowledge of this instrument accuracy, we can take the sigma squared from that, but in most cases, data analysis cases, we may not have been told what is the accuracy of the instrument used to measure the dependent variable. So, sigma squared also have to somehow be estimated from the data. We can show that we can derive a very good estimate of sigma squared by this quantity that is described here, which is nothing but the difference between the measured value yi and the estimated value yi hat, which is obtained from the linear equation. We have fitted a linear model. So, for every xi we can predict from the linear model what is the estimate of yi hat for every sample. Then we can take the difference between the measured and the predicted value of the dependent variable, sum squared divided by n minus 2. That is a good estimate of sigma hat squared, which is the error in the dependent variable. Now, why do we divide by n minus 2 instead of n minus n or n minus 1? Very simple, yi hat was estimated using the linear model. It had two parameters, beta naught and beta 1, which means that two of the data points have been used to estimate beta naught and beta 1, and therefore only the remaining n minus 2 samples are available for estimating this sigma squared. Okay. Suppose you had only 2 samples, then your numerator would be exactly 0. Because you have more than 2 samples, you have variability, and that variability is caused by the error in the dependent variable. That is one of the reasons that you are dividing by n minus 2, because 2 data points have been used to estimate the parameters beta naught and beta 1. Now, this particular numerator term is also called the sum squared errors or SSE for short, and so sigma hat squared is nothing but SSE divided by n minus 2. So, from the data, after you have fitted the model, you can compute this value and compute this SSE and obtain an estimate for sigma hat squared. So, you do not need to be told the information about the accuracy of the instrument used to measure the dependent variable. You can get it from the data itself. Okay. So, now finally, not only we have got the first moment properties of beta naught hat, beta 1 hat, as well as the second moment properties, which is variance of beta 1 hat and the variance of beta naught hat. We can also derive the distribution of the parameters. In particular, beta 1 hat can be shown to be normally distributed. Of course, because the expected value of beta 1 hat is beta 1, it is normally distributed with beta 1, the true unknown value of beta 1 as the mean, and the variance given by sigma. If you substitute the sigma hat squared here, you can finally show that this is nothing but I am sorry. So, this is unknown sigma squared divided by SXX. Okay. Sigma squared is essentially here we have derived this sigma squared by SXX is the variance of beta 1 hat. Now, if you do not know sigma squared, you can replace the sigma squared with this sigma hat squared SSE by n minus 2. Okay. So, once you have derived the distribution of the parameters, we can perform hypothesis testing on the parameters to decide whether these are significantly different from 0, and that is what we are going to do. We can also derive what we call confidence intervals for these estimates based on their distributional characteristics, that is the mean and the variance. Now, the first thing we will do is to develop confidence intervals. Confidence interval simply says what is the interval within which the true value, unknown value is likely to be with 95% confidence or 90% confidence. You can decide what size confidence interval size you need to have, and correspondingly you can obtain the interval from the distribution. So, if we want a 95% confidence interval, also known as CI, and it is two sided because it could be either to the left of this estimated value or to the right of the estimated value. So, we are obtaining the 95% confidence interval for beta 1 from its distribution, knowing it is normally distributed with some unknown variance. So, that we can actually derive from the from this particular range, which is the estimated value of beta 1, which is beta 1 hat, plus or minus 2.18 times the standard deviation of beta 1 hat estimated from the data. Notice this is very similar to the normal thing, which says that the true value will lie between estimate plus or minus 2 times the standard deviation. The reason why we have 2.18 instead of 2 is because we are no longer obtaining the critical value from the normal distribution, but from the t distribution, because sigma squared is estimated from the data and not known a priori. So, the distribution slightly changes, it is not the normal distribution, but the t distribution, and that is what we have pointed out here. This 2.18 is nothing but the critical value, 2.5% critical value, upper critical value with 12 degrees of freedom. Why 12 degrees of freedom? Because you have in this particular example we had 14 points and we use 2 of the points for estimating the 2 parameters. So, n minus 2 is the degrees of freedom, which represents 12. In general, depending on the number of data points, this value 2.18 will change. Okay. So, that changes the degrees of freedom of the t distribution, from which you should pick the upper and lower critical value. So, lower critical value is minus 2.18, the upper critical value is 2.18, 2.5%. So, the overall is 5%. This confidence interval represents the 95% confidence interval for beta 1. So, all we are going to state is that the beta 1 true unknown beta 1 lies within this interval with 95% confidence, that is what we are saying. Okay. Beta 1 hat can be estimated from data, S beta 1 hat can be estimated from data. So, you can construct this confidence interval. Similarly, you can construct the 95% confidence interval for beta naught from its variance. So, we are doing the same thing, beta naught hat plus or minus 2.18 times standard deviation of beta naught hat estimated from data, which is what we call S beta naught hat. Remember, S beta naught hat is sigma squared, which is estimated from data, multiplied by this square root of sigma xi squared divided by n times xxx, which is nothing but the square root of what we have derived in the earlier thing, with sigma squared replaced by the estimated quantity. That is all this these two terms represents, S beta 1 hat and S beta naught hat. So, having constructed this 95% confidence interval, you can also use it for testing whether beta 1 naught is the unknown beta naught is equal to 0 or not, or the unknown beta 1 is equal to 0 or not, which is what we will do. So, let us look at why would we want to actually do these hypothesis tests. We have fitted a linear model assuming that that there is a linear dependency between x and y, and we have obtained an estimate of beta 1 hat. Also, we have also fitted an intercept term. We may want to ask, is the intercept term significant? Maybe the line should pass through 0 0, the origin. Maybe the y variable does not depend on x1 in a significant manner, which means beta 1 hat is approximately equal to 0, that unknown beta 1 is exactly equal to 0, although we have got some estimate for beta 1 hat, non-zero estimate for beta 1 hat. So, the null hypothesis what we want to test is beta 1 equal to 0, okay, versus the alternative that beta 1 is not equal to 0. If beta 1 equal to 0, it implies that the independent variable x has no effect on the dependent variable. But on the other hand, if we reject this null hypothesis, we are concluding that the independent variable does have some effect on the dependent variable. Okay. So, this particular hypothesis test can be also reinterpreted as the null hypothesis implies beta 1 equal to 0, which means what we are doing is only a fit of yi is equal to a constant, whereas if we accept or reject the null hypothesis, then we are actually fitting a linear model with beta naught and beta 1 present. Okay. So, the null hypothesis represents the fit of a reduced model which involves only a constant, whereas the rejection of the null hypothesis or the alternative hypothesis implies that we believe there is a linear model that relates y to x. So, between these two models we want to pick whether the reduced model is acceptable or maybe the full model is to be accepted and the reduced model should be rejected. That is what we are doing when we test this hypothesis beta 1 equal to 0 versus beta 1 not equal to 0. Remember, beta 1 can be either positive or negative, and that is why we are doing a two sided test. So, we can do it two ways. We can actually reject the null hypothesis if the confidence interval for beta 1 hat beta 1 includes 0. So, notice that we have constructed the confidence interval for beta 1. So, this term beta 1 hat minus 2.18 may be negative and this may be positive, in which case this interval includes 0, and then we have to definitely we might make a decision that beta 1 is insignificant and actually the true beta 1 is equal to 0. On the other hand, if both these quantities, if the interval is to the left of 0 which is completely negative, or to the right of 0 which means both these quantities are positive, then this interval will not contain 0, and then we can make the conclusion, reject the null hypothesis at beta 1 equals 0, which means beta 1 is significant. So, from the confidence interval itself it is possible to make the reject or not reject the null hypothesis. So, we can extend this kind of analysis to even test whether beta naught is 0 or not. So, if the confidence interval for beta naught, this particular interval includes 0, then we will say that the intercept term is insignificant, otherwise we will say the intercept term is significant and should be retained in the model. Okay. So, let us actually when we do a final example we will see this. There are other ways of performing this test, and we will continue we will do that also, because that is very useful when we come to multilinear regression. In the univariate regression we have only these two parameters, but multilinear regression there are several parameters you will have, one corresponding to each independent variable, and therefore there will be lot more hypothesis tests you will do. Therefore, we will extend this kind of an argument to test for beta 1 equal to 0 or beta 1 not equal to 0 using what is called a F test, which we will go through. So, before performing this F test, to check whether a reduced model is adequate or we should accept a full model, we will use some definitions for sum squared quantities. Notice that let us say that we have a set of data. In this case we have the example of the number of units that were repaired and the time taken in minutes to repair the units by different salesperson, and we had 14 such data points, 14 such salesmen who have actually reported the data. So, the red points actually represents the data, and the best the linear fit using the method of least squares, using all the data points we got something, that is indicated by the blue line. Now, suppose we believe that a constant model is good, then we would actually fitted this particular horizontal line would be the best fit representing y bar. The best estimate of the constant model is the mean of y. For all values of x, our prediction, best prediction for yi is the mean value of yi, which means x has no relevance, beta 1 is 0. So, we will estimate the best constant fit for yi is this mean value. Okay. So, the red line represents the best fit when we ignore beta 1, the slope. The blue line represents the best fit of the data when we include the slope parameter beta 1. Now, let us look at certain sum square deviation. The deviation between yi and y bar, which is the red line, best fit of the constant, this distance is yi minus y bar, and sum square of all these vertical distances from the point to the red horizontal line, constant line, that is what we call the SS total or sum square total, which also represents the variance of y, yi minus y bar the whole square. All that we have not done is divided by n. If we had divided by n or n minus 1, we would have got the variance of y, but this represents the sum squared errors in yi when we ignore the slope parameter. That is another way of looking at it. The distance between yi and yi hat. So, now suppose we assume that the slope parameter is relevant, then we would have fitted this blue line, and for every xi, let us take this xi yi corresponding to this independent variable, the predicted value of yi using this linear model would be the intersection point of this vertical line with the blue line, which is represented by the blue dot, which is what we call yi hat, and therefore, this vertical distance between the measured and the predicted value is the sum squared errors, is called the SSE, yi minus yi hat the whole squared, and this is the total error if we include the slope parameter in the fit. Okay. So, the difference between these two quantities, SS total minus SS error, will be equal to what is also called the sum squared residuals, which is nothing but the predicted value minus the mean value y bar, sum squared over all the data points. Now, we can show that SST will always be greater than SSE, because SSE was obtained by fitting two parameters, therefore, you should be able to reduce the error. Okay. Maybe marginally, but you will be always able to reduce the error. So, SS total is the will always be greater than SSE, and therefore, this difference SSR will also be positive. All of these are positive quantities. Now, one can interpret SS total as the goodness of fit if we assume a constant model. We can interpret SSE as the goodness of fit of the linear model, and therefore, we can now use this to perform a test. Literally, intuitively, we can say that if the reduction by including the slope parameter, that is SST minus SSE, is significant, then we conclude it is worthwhile including this extra parameter, otherwise not. This can be converted into hypothesis test, formal hypothesis test, and that is what is called the F test. So, what we are doing is, as I said, that SS total is a measure of how good the reduced model is, which reduced model here implies a constant model, whereas SSE represents how good the linear model if we include the slope parameter. So, we are asking whether the reduced model should be accepted, which is the null hypothesis, or should be rejected in favor of this alternative, which is to include the slope parameter. So, as I said, the F statistic for doing this hypothesis test is to compute the difference in the goodness of fit for the reduced model, which is always higher, minus the goodness of fit SSE for the alternative hypothesis. So, this represents the sum squared errors for the reduced order model fit, SSE represents the goodness of fit for the alternative hypothesis fit. This difference, if it is large enough, as I said, then we can actually say maybe it is worthwhile going with the alternative hypothesis rather than the null hypothesis. So, SSR, which is the difference between this, should be large enough. So, normalization, what the denominator represents in some sense a percentage, SSE is the error obtained for the alternative hypothesis. Remember, because of the difference in number of parameters used in the model, we have to take that into account. The numerator SST has n minus 1 degrees of freedom because we are fitting only one parameter. This has n minus 2 degrees of freedom because we are fitting two parameters. So, the difference actually means it is only one extra parameter. So, there is numerator which is SSR has only 1 degree of freedom, which is n minus 1 minus n minus 2, whereas the denominator SSE has n minus 2 degrees of freedom because it has two parameters which is fitted. So, we are dividing the SSE by n minus 2, the number of degrees of freedom. So, average sum squared errors per degree of freedom, that is what we are saying, okay. And that is your normalization. SSR divided by this normalizes this quantity, and we can show formally that it is an F statistic because it is a ratio of two squared quantities, and each squared quantity is itself a chi-squared variable because it is a square of a normal variable. Therefore, this is the ratio of 2 chi-squared, and we have seen in hypothesis testing the ratio of 2 chi-squared variable is an F distribution with appropriate degrees of freedom. The numerator degrees of freedom is 1, the denominator degrees of freedom is n minus 2. So, if we want to now do a hypothesis test using this statistic F naught, we compare F naught with the critical value from the F distribution. Notice F is actually a positive quantity. So, we do a one sided test. If we choose the level of significance as 5%, then we choose the upper critical value from the F distribution with 1 and n minus 2 degrees of freedom and 5% level of significance, or what we call the upper critical value is probability is 5%, 0.05. So, once we get this from the F distribution, we got this threshold, and if the statistic exceeds the threshold, then we will reject the null hypothesis and say the full model is better than the reduced model. We will accept the full model, or we say that we reject the reduced model in favor of the full model. The slope parameter is worth including in the model, we will get a better fit. That is how we actually conclude. So, there are now several ways for deciding whether the linear model that we have fitted is good or not. We could have used the R squared value. We said that if it is close to +1, then we should that is one indicator that the linear model may be good. It is not sufficient, what I call sufficient to conclude, but it is good indicator. We can also do the test for beta significance of beta 1. If we conclude that beta 1 is not significant, then maybe then a linear model is not good enough, we have to find something else, or we can do an F test and conclude whether the including the slope parameter is significant. So, these are various ways by which we can decide that the linear model is acceptable or not, or the fit is good. We cannot stop with this, we have to do further tests, but at least these are good initial indicators that we are on the right track. So, let us apply this to the example of repair of or the servicing problem, where we have 14 data points and the time taken and the number of units repaired by different salesmen are given. So, in this case we have these 14 points which I have showed. We have fitted the data using R. Remember that LM is the function which we should call for fitting a linear model, and here we are predicting the dependent variable is minutes and the independent variable is units, and once we have fitted this using the R function, it gives out all of these output, and it gives you the coefficient. The intercept term turns out to be 4.162, the slope parameter turns out to be 15.501, okay. But also it also tells you what is the standard deviation, estimated standard deviation of this parameter, which is S beta naught hat of the intercept. It also tells you what is the standard deviation of this estimate for beta 1, which turns out to be 0.501, 505, all of this calculated from the data using the formulas we have described. Now, once it has given out, we can actually now perhaps construct confidence intervals and find out whether these are significant or not, or R itself actually tells you some thing whether these, if you run a hypothesis test, whether you will conclude whether beta naught hat is significant or beta 1 hat is significant, and that is indicated by what is called this p value that it has reported. So, if you get a very high value, t value represents the statistic which you have again described earlier. So, it has computed the statistic for you for beta naught hat and the statistic for testing whether beta 1 equal to 0 or not, and it has computed the statistic value, and it has compared with the critical value the distribution t distribution with the appropriate degrees of freedom, and concluded that the upper critical or the probability is 0.239, which means if you get a very high value for this, anything greater than 0.01 or 0.05, it means you should reject the not reject the null hypothesis. On the other hand, if you get a very low value, it means you should reject the null hypothesis. With greater confidence you can reject the null hypothesis. So, in this case all it is saying is, if you choose a level of significance 0.001, you would not reject the null hypothesis. If you choose 0.05, you will not reject the null hypothesis. If you choose 0.01 as your level of significance, you will not reject the null hypothesis. So, that is what the star indicates, at what level of significance will you reject it. Whereas, in the case of beta 1, you will reject the null hypothesis, which means you will conclude that beta 1 is significant even if you choose very low significance value 0.05, 0.01, 0.001 or even lower value. In fact, up to 10 power minus 13 you will end up rejecting the null hypothesis. Very low type 1 error probability if you choose also, you will reject the null hypothesis. So, therefore, you can conclude from these values that beta naught hat is insignificant, which means beta naught hat is equal to 0 is a reasonable hypothesis, beta 1 hat is not equal to 0 is a reasonable hypothesis. Let us go and see whether this makes sense for this data. We know that if there no units are repaired, then clearly no time should be taken by the sales repair person, which means because he has not taken any time for servicing, yes, because he has not repaired any units. So, this line technically should pass through 0 0, and that is what we have said. But however, we went ahead merrily and fitted an interceptor, but the test for hypothesis says you can safely assume beta naught the intercept is 0, it makes physical sense also, and we could have only fitted beta 1, that is good enough for this data. Okay. So, perhaps you should redo this linear fit with beta naught 0 and only using beta 1, and you will get a slight different solution and you can test again. So, another way of deciding whether the significant whether the slope parameter is significant or not is to look at the F statistic. Notice the F statistic is very high and this p value is very low, which means you will reject the null hypothesis that the reduced model is adequate, implying that you should use beta 1, including beta 1 is very good, you will get a better fit using beta 1 in your modeling. So, the high value of test statistic indicates that you will reject the null hypothesis, or a low value of p value for this F statistic indicates that you will reject the null hypothesis even at a very low significance level. Okay. You can also construct the confidence interval for beta naught and beta 1, and from the earlier thing we say approximately it is estimate plus or minus 2.18 times the standard error, and that is what is in 4.1 plus or minus 2.18 times 3.35, and that turns out to that gives the interval confidence interval minus 3.148 to 11.472. That means with 95% confidence we can claim that the true beta naught lies in this interval. Similarly, we can construct the interval confidence interval for beta 1 hat 95% confidence interval, and it turns out it is 15 plus or minus approximately 2 times 0.5, which is 14 and 16.6. Now, clearly the interval confidence interval for beta naught includes 0, and therefore, we should not reject the null hypothesis beta naught equal to 0. Okay. We should simply accept that beta naught perhaps is equal to 0, whereas the interval for confidence interval for beta 1 does not include 0. So, we can reject the null hypothesis that beta 1 equals 0, and the slope is an important parameter to retain in the model. Now, all this we have done only for a single thing. We will be extending it to the multilinear case, and we will also look at other assumptions the influence of bad data and so on in the following lecture. So, see you in the next lecture.